I'm a student here at Eastlake High School, and
What can I help you with today?
I'm in a predicament right now.
What's wrong?
So I have this huge chapter test for 17 and 19 in my physics class, and I feel totally lost.
Well, if you definitely come to the right guy. What in particular in chapter 17 and 19 would you like to review?
Really, I've kind of been slacking off, I can be honest, and I feel like it'd just be nice to refresh the whole chapter.
Well, I do have to go somewhere soon, but I guess I could stick around and help you a little bit.
Yeah, thanks, it would mean a lot.
Go ahead and take a seat anywhere. Before we start this chapter, you should probably grab like a notebook and a pencil
Oh yeah,
to get started.
sure. Just one sec, I'm looking for a pen or a pencil. This one.
You all set?
Yeah.
For the start of chapter 17, we're going to be talking about the law of reflection. So basically, for example, let's say we had a smooth surface such as a mirror.
Okay.
If, let's say we had a light beam hit this mirror at about a 70-degree angle,
Okay.
do you know what the ray would be called?
Wouldn't it be called like the incidence ray?
Yeah, it would be. Now, since it is hitting an object such as a mirror, which is a smooth surface, and mirrors tend to reflect things such as light, the ray would bounce back at a 70-degree angle, parallel to the incidence ray. You know what the ray that would be bounced off the mirror would be called?
So it wanted to be called the reflective ray.
Yeah.
Now, what if let's just say that the reflector is not a smooth surface.
Let's say we had a rough surface, and the incidence ray hits that spot right there.
Okay.
The ray would bounce back in almost scattered, random patterns. Now, do you know what this kind of reflection would be called?
I have no idea.
It would be called a diffuse reflection. You might want to write that down.
Okay.
All right, let's go back to that first reflection we were talking about, which is the regular reflection, where we had the incidence ray and the refracted ray. Now, you notice how I said that the reflected ray, the incidence ray came in at a 70-degree angle, which would also mean that the refracted ray, since, parallel to the incidence ray, would come in at a
70-degree angle.
70-degree angle. Now, do you know what this angle right here would be called?
Isn't that like the angle of refraction?
Yes, because this is the refracted ray, and that's the incidence.
Okay.
Now, this angle, you know what that angle would be called?
The angle of incidence?
Yep. And in your book, it says here also that the angle of refraction is the angle that the refracted ray makes with the normal to the surface.
Okay.
If the angle of refraction is smaller than the angle of incidence, then the new medium is said to be more optically dense.
Okay.
Alright. Now for the refraction of, let's discuss refraction of light. You know what? Matter of fact, I have a PowerPoint that I put together for my class for them to take notes for tomorrow's lesson. So why don't we go back to my classroom and I'll actually let you see that PowerPoint.
Cool, great, let's go.
So with the refraction of light, the angle of refraction is the angle that refracted ray makes with the normal of the surface. And materials with larger indices of refraction with respect to other materials optically is the definition of optically dense. When a ray of light is being refracted, the light beam is being bent towards the normal. The ray that hits the object is the incident ray, while the opposite ray is the refracted ray. When a ray passes from an object such as glass back into the air, the light is actually being refracted away from the normal. If light hits an object at the perpendicular, the angle of refraction is 0, along with the angle of incidence. Snell's law. Snell's law is the ratio of the sine of the angle of incidence to the sine of the speed of refraction is a constant. And the index of refraction is the ratio of the speed of light in a vacuum to its speed of material. In 1621, Dutch scientist Wilbur Snell came up with an equation to answer the question as to why the angle of refraction depends on the angle of incidence when light passes from one medium to another. The equation goes n equals sine of theta subscript 1 over sine of theta subscript 2. Now, n is obviously the index of refraction, when the sine of theta subscript 1 would equal angle of incidence and sine of theta subscript 2 would equal angle of refraction.
Okay.
The index of refraction is a measure of how fast or how much light bends when it passes into a medium from the vacuum, as I said. The index is also a measure of how fast light travels into the medium. The equation to find the index of refraction is n equals c over v. In the equation, c is the velocity of light in a vacuum, and v is the velocity of light in the medium, with n obviously being the index of refraction. Total internal reflection. This occurs when light is incident on the boundary to a less optically dense medium at an angle so large that there is no refracted ray. The critical angle is the incident ray, or the incident angle, unique to a substance that causes the refracted ray to lie along the boundary of the substance. When light does pass from objects such as glass into the air, the beam is refracted away from the light. That means that the light angle of refraction is bigger than the angle of incidence. This leads to total internal refraction, which has no refracted ray. Any questions?
So my question is, why does it have no refracted ray?
The reason there's no refracted ray is because when light passes from a more optically dense medium to a less optically dense medium at an angle so great, there just really there can't be a refracted ray.
Oh, that makes sense.
Dispersion of light. Dispersion is variation of the speed of light through matter resulting in separation of light into a spectrum. Sir Isaac Newton was the first person to discover how the colors are actually formed. He learned sunlight separated into the spectrum of colors when passing through a prism. To prove this, he took one prism and shined white light through it, where all the colors would show. He then set up another prism next to the original prism with a lens separating the two. The colored light passed through the lens and then the prism, producing white light.
Go ahead.
To continue on from the previous slide, when passing through a prism, every color is actually bent a certain specific amount. Red light is bent the least when going through the prism, while violet light is bent the most. This means that the index of refraction for red light is pretty small, while the index of refraction for violet is pretty big. Also, glass is not the only material that can disperse light. As a matter of fact, diamonds have the highest refractive indices of any material, along with one of the largest variations in the index.
Now we're going to get.
Now we're going to be moving on to chapter 19, which is diffraction of light. The diffraction of light was discovered by Italian scientist Francesco Maria Grimaldi. Diffraction is the slight spreading of light around barriers. English physician Thomas Young decided he wanted to use diffraction to allow him to make precise measurements of light's wavelength. Young created two closely spaced, narrow slits in a barrier and shined a beam of light directly at the slits. The light that shined onto an observer screen on the other side of the slits produced bright, dark bands,
which would be known later on as interference fringes.
That is known as also Young's two-slit experiment. Now, interference fringes, like I said, are a pattern of dark and light bands on the screen. Later on in his experiment, he used monochromatic light, which is a light only one wavelength. And coherent waves are waves that are in phase, meaning wave crests and troughs are reach the same point at the same time. But to continue on from his two-slit experiment, Young extended the pattern of dark and light bands. Interference fringes was a result of constructive and destructive interference of the light waves from the two slits. He then placed one narrow slit in front of the monochromatic light. The light diffracted through the one slit, and then diffracted through the original two slits and also created a pattern of bright and dark bands. Now, we talked about double slit diffraction. Now, let's get into single slit diffraction, which is pretty similar to double slit. As you can see in the picture, in single slit, there's pretty self-explanatory. Just one slit is being used and the light is being shined through that one little slit onto an observer screen. And as I said earlier, when light passes through a single small opening in a double slit experiment, the light is diffracted, creating a pattern of dark and bright bands. However, when a beam passes through just one single small opening in a single slit experiment, the pattern created is a wide, bright central band with thinner bands on each side. When we're talking about measuring the wavelength of light, if you actually make the width
Of one of the slits smaller.
the distance between the dark bands become wider. You can also make this distance wider if you use light with a longer wavelength. This helps make the interference fringes more noticeable when the beam passes through the small openings. Resolving power of lenses. The Rayleigh criterion. When the central band of one star falls on the first dark band of the second, the two stars will just be resolved. The Rayleigh criterion helps you to be able to tell if there are actually two stars in the sky and not just one when using a telescope. Diffraction connections limit the resolving power of microscopes along telescopes. The wavelength of light can always be reduced. The objective lens of a microscope cannot be enlarged. Microscopes used by biologists usually use blue or violet lights to illuminate their objects because the diffraction pattern formed by blue light is narrower than that of red light.
Now, Mr. AJ Dover, that's going to wrap up our PowerPoint. Do you have any more questions before you head out and you have to go worry about studying for that big test?
Nope. Thank you so much, Mr. Lamont. It helped a lot.